All right, this is just chatting. So people, panic about greedy tests. And let me tell you, there's, the first greedy test, lots of people get zeros. They just crash and burn, right? So, and the point is that most of the issues are the same, right? And it's, in some ways it's going to be even easier for you because I've sort of taken the loop invariant stuff away from the key game, right? We've taken the topic of greedy algorithms and kind of cut it with this game in the middle. And we proved that if you prove the game, then the greedy algorithm works, right? So I might test you on that. In fact, here's something, right? So if it's an in-person class, a test, I'm more likely to test you on that because you will have to have memorized it, right? If it's a take-home test, it would be harder to test you on that because you just look it up, right? But what will definitely be in the test is I give you a new problem and you have to play the game, right? So I'm going to give you a new definition of what is an instance and what is the solution to an instance and what are the costs, right? And so what you need to have in your brain is sort of this, in my opinion, you want this abstract idea that a greedy algorithm takes an instance right? And then you want to map into your brain after you read my question. You have to say, what is the instance? All right, now anytime greedy algorithms talk about instances, it's a sequence of objects. What are the objects? What are the relationships between them, right? You have to plug that into the new question, into your framework, right? One way I very quickly give zeros when I'm marking is if what they're writing doesn't seem, then they don't even know what the instance is. They don't know what the solution is. They don't know what the cost of the solution is, right? More or less, you can take the framework of my proofs and you have to plug in. In fact, I haven't rewritten the those one-page things. What are they called? Steps or something, right? So that's still of the framework of loop invariance, but I'm sure you can find the game. And I think I even have it bold, the things that you have to substitute in, right? You have to substitute in what is an instance, what is a solution, right? And you have to, I probably will not give you what the algorithm is. So you'll have to think which object, what is the greedy criteria, right? Which object do I consider first? And how do you make a decision about that object? And like we did with loop invariance, if I feel that you might not get that, then I will give you hints or give it all to you, right? Sometimes what I've done, which is I think is particularly fun, is I will give you 2 or 3 greedy algorithms. And as you can imagine, 2 of them don't work. And so there'll be a question, which 2 don't work? And for those, you give me a counterexample. And then you prove that the 3rd one works, right? So, right, and what do I mean by the changing step, right? That is the game, right? This is an old slide, but the changing step is the game, right? We have the fairy godmother's ST minus 1. We have to change it into ST, right? That is the hard part, right? And then we have to say now we have this new thing ST minus ST, right? You have to prove that it's still valid, right? It was valid, it's still valid. It extended ST minus 1. You have to prove that it extends XT as well. Oh, maybe I actually changed this, right? I used to say optimal, right? And I've changed it to it's at least as good as ST minus 1, yeah? No, no, no. You need the right one, right? And all right. So that's a good question, though. So I would say, if when I'm making up a test, if there's only one obvious greedy criteria, I might not give it to you, and I might make you come up with it. But like in this example, there are a few greedy criteria, all which seem obvious, and only one of them works, right? In that case, I might warn you, hey, dude, there are a bunch of greedy criteria out there. In fact, if there are three obvious ones, I might list, here are the three obvious ones. And I'm going to tell you only one of them works, right? So be warned, and prove to me that two of them don't work, right? I think it would be unfair if there were three obvious greedy criteria and I didn't let you know that. And then what you would do is you would spend half the test proving that one works when it doesn't work, right? And that might be fair for me to do if you had 24 hours. It would be absolutely not fair to do if you only had an hour and a half, right? Because I don't want you wasting time, right? That's my thinking on it, right? Everybody kind of get that? So here, this is saying, yeah. Yeah. So the running time of the greedy algorithm is going to be the n log n short, and then usually it's linear time after. All right. So this is just thinking we're making decisions, right? We start off here and saying, do I take the first event? Do I not take the first event? Right? Right? It's a sequence of decisions, and this is just trying to draw a picture of then the leaves are full solutions, right? If you follow any path down this tree, then it's like the game of 20 questions, right? Is the solution an animal, vegetable, or mineral, right? You take a path. Does the solution take this event or does it not take this event, right? You follow a path down, and then this path down the tree leads, you've answered all the questions, you make all the decisions, so now you have a full solution, right? Does that make sense? Everybody understand this decision tree? And so I'm making some of the leaves purple because those ones are optimal solutions, right? I.e. they have the same value and they're better than all of the others, right? So recursive backtracking and backtracking is you'll try some things and then you'll backtrack and you'll try some other things and you'll backtrack, right? So we're not doing that. What does the greedy algorithm do? It just barrels down one path blindly, making these greedy choices each time, right? And so just kind of from this discussion, it seems surprising that such an algorithm will work, right? All right, so suppose the algorithm has made some decisions down to some point. So it's made the decisions AT minus 1, which brings it to here, right? And that effectively burns all of these bridges, right? These solutions down here are no longer possible, right? Everybody following this picture? And what is the fairy godmother doing for us? She is holding one optimal solution, right? That's right. What does she want? She wants the best for the algorithm. She wants the decisions that he makes not to prevent him from an optimal life, right? So anyway, she's holding this optimal solution, ST minus 1, and you can see it's consistent with what the algorithm has done, right? And then here we have our prover, and his job is to make sure that the mom is happy, and right? So what the fairy godmother has in mind here is for her son to be a lawyer, right? But then look at the algorithm makes this decision. And so that burns this bridge. He can no longer be a lawyer, right? And so that's out. But look at, he can still become a doctor. And so the job of the prover is say, Mom, it's not so bad that he can't be a lawyer. He can still be a doctor, and she'll be okay, right? So the prover switches the mom from the view of him being a lawyer to the view of him being a doctor, and she's still happy for another day, right? Does that make sense? Right? As long as they're, when is the mom going to be happy? As long as from today there's a path she can follow, that her son can follow, that will be reasonably good, right? Or optimal. All right, so here's just another, I keep adding slides to, hopefully it makes the world happy, right? Here are the decisions made by the algorithm so far, right? And what does the algorithm do based on what it's done so far, right? It decides what the next object will be, right? Oh, based on the past, it uses the greedy criteria to see which object it's going to see next and makes a decision about it. And so we get the new thing, right? And so here's the algorithm. And right here, no decisions have been made yet. And here we have the final output. And here we have a full solution. And here's a loop invariant that we haven't, right? So this says there exists an optimal solution that is consistent with that, right? And so as we go along, the prover sort of takes her solution, takes what the algorithm is doing, and modifies it into being ST, which needs to be, right? We give a paragraph which describes the bulk of your work is to describe this paragraph that takes this as input and gives that as output, right? And then you have to prove that it's, oh, here, I've modified these as well, right? So you have to prove that this is still a subset, it's still just as good, right? Everybody buy that? And that maintains the loop invariant, right? And so you kind of get this picture, right? Yeah? Yeah. We go from to 4, so we still have some time. Yeah.
But we don't really know that there's an optimal solution available. Then what happens?
Are you talking about this tree over here? Yeah. Well, I guess the goal is for if the algorithm came down here, where's our algorithm moving? The algorithm came down here, and there were no purples down here, then the algorithm would have failed. It wouldn't know. It would just bumble along, and it would give this answer, and it's just not optimal. So such an algorithm is an algorithm that doesn't have the greedy algorithm, doesn't work, right? It's like you commit to if you're trying to make 6 cents and you commit to the 4 cents, then you burned all your bridges because the optimal solution doesn't have a 4, it has a 3 and a 3, right? So there are definitely algorithms that don't work, but in the algorithms that do work, as the loop invariant is that no matter how far down the algorithm has moved, there's always a purple node below it, right? I mean, that's one way of stating the loop invariant. Wherever in this tree the green node is, in its subtree, there's at least one purple, right? it would put up a panic sign and says, hey guys, here's an example where there's an input and the answer that the algorithm gives isn't optimal. Right? This would be an example where the algorithm doesn't give the optimal solution. It depends on how deceptive it was. It could try to fake things, or it could be honest and say, hey guys, sorry, the algorithm doesn't work. Let's hope you'll be honest. Right? And they could go back to the drawing board and try to come up with a better algorithm. Or maybe what he'll try to do is say, yeah, it doesn't give an optimal algorithm, but optimal solution, but maybe it's a solution that's good enough for us, right? Maybe it's within a factor of 2 of optimal. Or no. Yeah. So you have to. What I would do is I would say, I tell you what the problem is, input solution costs. You will say what your greedy criteria is. You'll say whether you choose to take it or not take it. That defines the algorithm, right? And then if all I make you do is none of that proof stuff, I just make you do the game, then you'll say, I'm jumping to the middle of the algorithm. The algorithm, we have AT minus 1. This is what the algorithm has done so far. And I would draw a picture of it, right? Here's an example. You want your proof to work no matter what the picture is, but a picture helps, right? You draw the right picture, it helps, right? So you draw a picture of AT minus 1. Then the fairy godmother is holding ST minus 1, right? So you say, hey, fairy godmother has ST minus 1. It's a valid solution consistent with what the algorithm has done. Ideally, it's even optimal, right? And then you'll say the algorithm does the next step, and you draw that in your picture. And then you need a paragraph saying how you change ST minus 1 into ST, right? And you'll do it proof by picture. You'll say what you would have done for this picture. And then you give a paragraph in English as well that's clear enough to say what's going to happen in all cases, right? Add this event, drop all events that conflict with it, right? And then you'll have a paragraph which proves that your ST is still valid. You have a paragraph which proves that your ST is still consistent with what the algorithm is doing. It's at least as good as what the optimal, what the fairy godmother has, right? Those are your paragraphs. Yeah, everybody kind of good with this big picture, right? You guys will get restless when I run out of time, right? Because I can't see what time it is. We got a few more minutes. 3:40. Good. We have at least another 10 minutes. All right. Here, this is just right. How do you establish the loop invariant at the beginning? As well, this guy doesn't have any decisions. This is kind of the empty set, right? So the empty set is a subset of everything, right? And over here, these guys are equal. Everybody kind of good with these pieces? Just running with that picture. Oh, remember this slide I made years ago for you guys? This was how do we maintain the loop invariant, right? So I'm standing here. I know the loop invariant is true. I know I have ST minus 1. I have to produce ST, right? So my first step is to kind of make progress, whatever that means. And what I'm going to do here in my first step is I'm going to say, hey, my little brother just made some decision about object T. And the fairy godmother needs to make the same decision about object T, right? So that's the first step, right? And so that just says, take the fairy godmother solution and add or modify the decision about this object here, right? But you'll see the problem is we fell off the path. Why? Because the solution might not be optimal anymore. It might not be valid anymore. right? So you have to come back onto the path. And how do you come back onto the path? Well, the fairy godmother complains, dude, you messed up my solution. It's not optimal anymore. It's not valid anymore. And the prover says, hey, don't worry, I'll try to fix it. And how does he fix it? Well, he's going to have to find some other objects in her future, right? And that the algorithm hasn't considered yet. Going to find some other objects that aren't in AT, right? That can somehow conflict with these changes. And the prover is going to say, change the decision made by these other objects, right? So, right? Or maybe it's no longer valid, right? It conflicts. And it's no longer optimal, right? So if it's no longer optimal, we have to find some object to put back in. And it may be a couple of objects that you have to change, but usually it's only one. In fact, I've never had never is a big statement. So rarely have I had a positive conversation with my father about mathematics. I asked him once, you only learn about matroids where you swap one thing in and one thing out. But we have, in computer science, we have such a broader definition of greedy algorithms that I'm not sure they all fit into your matroid world. And he just was not willing to talk to me about it. So I don't know the answer to that question. But certainly it feels like you might swap more than one. It might not be a matroid, but we can handle that. All right, so here, what are you doing is you have the ST minus 1. You definitely have to add in what the algorithm did, and then you'll probably have to modify something else, right? Does that make sense? To get it back on the path. And then she's happy again, right? It's valid again, it's optimal again, and we're good, right? Does that make sense? This is about past and present, right? That's the past. Here's the present, right? And here's the future. And so the general, and she's consistent with that, right? So the first step is making that consistent, right? That was the object T that has to be fixed. And then, right, you don't change any of that, right? You don't change the past or right? So then it's the fairy godmother's future that we have to change, right? So now you want to prove is this new thing, which is the new one? These numbers are kind of funny, but anyway, what's the right? We know that if you're trying to find out if it's valid, remember we know none of this stuff conflicts. Why? Because the algorithm is doing it, right? And she's the same down here, right? Once we've swapped those don't conflict. In some ways, these don't conflict, right? Because that was all in her future, right? It's kind of this is the area where you have to be looking for conflict. You know what I mean? It's kind of, this is very abstract and vague, but you can kind of see from our examples, right? Everybody good? All right, so you grab some other object and change it. Is it optimal? Well, you have to show it's at least as good as that. And these you can go over. They're just answers that students have given that were wrong, right? And I think we've talked about all of this stuff, right? You can read through answers on your own that students have given, right? Usually what happens, I'll tell you what, when I'm reading people's solutions, and I've been doing this, since longer than you've been born, I see people write down words that I have said. It's like, yeah, I remember saying that, right? But I have to dive in deeper and say, did the student understand it? Or are they just writing down words? And sometimes they'll write down words that I said and put it in places that have nothing to do with what we're talking about right now, right? So I have to say, is it relevant? And did they understand it? So if they say something like, oh, we changed it to ST and we have to make sure that there's no conflict. All right, great. Well, what does that mean, right? Well, if the problem is to be valid, you have to have that up to 92 cents, then you have to make sure it still adds up to 92 cents. Don't just say, assume that I haven't taken my own course, right? In fact, the TA hasn't, right? So don't use words that you don't define, right? Don't suddenly talk about conflict. Don't ever talk about what the next object is that you're dealing with in your test, unless you say, hey, it's an event. Hey, it's an edge. Hey, it's right? Relate it back to the problem at hand. You know what I'm saying? Anything you can put in there to convince me and the marker that you are doing more than parroting the words that I've said. You know what I mean? So anyway, I don't think there's anything else in there. You can read them on your own. And I think we're probably done with time. So there are a lot of extra slides here. Who knows what? Those are probably, all these slides. Do you know when I make slides like this? I bet you I just finished marking a stack of exams this much and I hated you. Right? It's like, how could you do all of these wrong things? How could you do that to me? I take it as a personal insult. All right, so I think we're done. Have a great, today's Wednesday. Oh, so Friday, I will be here and I'm not covering any material. We will be doing whatever you want me to do. In fact, that when we were doing those room slides, they were probably made in real time on a Friday, right? So how is anybody out in the outside world? Are you reasonably happy? Thank you. Yes, thank you. Look, it works. Thank you. Hey, people look happy. That's good. Bye, world. I didn't hear from you. I hope you were good.